So now let's move on to how we get organized within the human body. And so for this one, we're going to talk about the different levels of organization, as well as talk about the different organ systems and some of the organs and the major functions in each of those. So when we're talking about structural organization, we go from the simplest level to the most complex. And so if we start at the top of the list, this is the simplest or the smallest level of complexity. And as we move down towards the bottom of the list, we're getting more and more complicated. So each of these levels kind of stacks on top of each other. So the basic one, at least for us, the most basic one are going to be things like atoms and molecules, the chemicals that make up living things. And that's as simple as we're going to get when it comes to organization. And chemicals are organized, right? Molecules are organized. They have a structure. It's very regulated. It's very, it's not going to necessarily change unless a chemical reaction occurs. Water molecules in one area are going to look just like water molecules somewhere else. We can then arrange these chemicals, we can arrange these molecules to form cells. That's when we get to our next level, which is the cellular level. We're getting a little more complicated. Now we have lots of different chemicals coming together in very specific arrangements to form a cell. These cells then come together to form tissues. So tissues are going to be cells that are similar in appearance and function, that work together to perform the same function. And then these tissues can be arranged to form an organ. So for example, with the organs, we have a stomach, right? That stomach is made of different types of tissues, right? It has, we have muscular tissue that forms the muscularis level. We have epithelial tissue, right? We have all these different tissues that come together that each tissue kind of contributes something unique to that organ, but overall contributes to the major function of the organ. And then organs come together to form a system, and multiple systems come together to form the entire organism, like an entire person. Right, so they all rely on each other, right? So we're at the very top here, and the chemical level is very simple. We have oxygen, we have hydrogen, we can form water molecules, we can form whatever chemicals, whatever molecules we need. Those chemicals come together to form a cell. The cell is more organized. It's very, very put together. It's not just a bunch of chemicals just free floating, right? There's organization to it. There is a specific pattern to it. Those cells come together to form a tissue, right? Again, a bunch of cells that are very similar in how they look and in the jobs they do, and then different tissues can come together to form the organ. In this case, we see a bladder, that's our organ. We see different types of muscle. We'll also see like epithelial and connective tissues as well. And then in this case, since we're looking at the bladder as the organ, our organ system is the urinary system. And we see that it's not just the bladder, but also the ureters, the kidneys, and the urethra. And then the organismal level, that would be the person who has that urinary system in them, right? That's working with all the other organ systems in the body. So here's some of the different organ systems we're going to be looking at throughout the semester. We're going to be looking at the integumentary system first. That's going to be our very, very first one, which is basically like the skin and its accessory organs. We're going to be looking at the skeletal and the muscular systems, so bones and muscles. We'll be looking at the nervous system, which we think like brain and nerves, the endocrine system, where we think hormones, the cardiovascular system, where we think the heart and all the blood vessels and blood. We'll also look at the lymphatic system, the respiratory system, the digestive system, the urinary system, and then both the male and female reproductive systems. So what are the functions of human life? Some things we're going to be able to accomplish when we get through this section is we're going to be able to talk about the importance of organization so that a human can actually function. We'll talk about metabolism, anabolism, and catabolism. And then we'll talk about human responsiveness and movement, and then talk about some terms, growth, differentiation, and reproduction. So what are the functions of human life, right? These are the things that you have to be able to do to be considered alive, basically. We need organization, so you have to be organized like cells and tissues and organ systems. You need to be able to conduct metabolism, where we're talking about all of the chemical reactions happening within the body. Responsiveness is another function, meaning we respond to things, both things that happen within our body, but also things that happen in our environment. So, for example, if the carbon dioxide level in your blood is increasing, then our body can respond by increasing respiration, so to speak. We can also respond to things that happen around us, right? So as you're listening to this, you're reacting, you're doing something. Maybe you're taking notes. Maybe you're thinking about what I'm saying. Or, if you hear your own name, you turn your head and face wherever the sound came from. Movement, we all move to some degree, so we can move, like if I were to throw something, right, at someone, they could catch it or they could duck out of the way. And then development, right? None of us are the same as when we were born. I hope not, right? None of us were born as fully formed adults. We were infants, and then we went through periods of change to become an adult. So we're clearly a lot bigger, we weigh more, we're taller, we have a bigger frame, like a bigger bone frame. Our bones even have changed, right? Going from a more cartilaginous base to an ossified, more bony base. Lots of things happen, right, over the course of our lifetime. And that's development, right? We're changing throughout the course of our lifetime. And then reproduction. And again, this is a general function, so we're not saying that if you don't reproduce or can't reproduce that you're not a human, right, or you're not alive. But in general, the human species has to be able to reproduce to be considered alive, right? And so we see that because people have children. So let's talk about homeostasis. Homeostasis, we already kind of defined, saying that we have these parameters we have to stay within, that we can only be so hot or so cold, we have to stay within that range. Same thing with like pH, same thing with a laundry list of things in our body. And the question is, how do we do that? How do we maintain homeostasis? How do we stay within those boundaries? And so we're going to talk a little bit about negative and positive feedback that can help us either stay within homeostasis or on some occasions actually leave homeostasis. There are some occasions where that's actually the beneficial thing. It's not as common. Negative feedback is the more common way to, common reaction or common feedback that we see within the body, but there's some cases where positive feedback is absolutely necessary. And so we'll talk about an example for each of those. So our body is always monitoring its internal conditions to maintain homeostasis. So think of it like if we're thinking temperature. If you're trying to keep your house at a certain temperature, you have a thermostat, right? That thermostat and the system you have in your house is able to detect what temperature your house is at and then adjust itself. Should we heat the house? Should we cool the house to keep it within that range? And so we kind of have a similar thing within our own bodies for all these different components that we're measuring, right? And so rather than call it a thermostat, we have what's called a set point, right? So the set point is kind of the value that's considered normal, right? So that's our normal value. That's what's considered normal and healthy. And we can fluctuate a little bit without anything going on. But if we go too far from that set point, then our body's going to have to do some sort of action to bring us back to that set point. So for example, our set point with body temperature is 98.6. That's the set point. That's the value, kind of like what we would consider normal on a point, on a single point. The normal range is what's considered normal or healthy, give or take from that set point. So for body temperature, for example, 97 to 99 degrees. As long as you're in that range, you're considered normal and stable and healthy. So, you don't have to stay 98.6 degrees Fahrenheit all the time. If you go to 99, you're not going to notice. You're not going to feel different. You're not going to feel sick. And no one's going to consider you sick if they were to see that on like a thermometer. Now, if you leave that, right, if you leave that range, right, so for example, we're talking temperature, if you leave that range, your body gets too hot or too cold, then we're going to have negative feedback come in to bring us back to that normal range. So here, right, I'm going to talk about the general concept on the left first, and then we'll talk about the specific example on the right. So let's go ahead and look at the left side first. So we have some sort of stimulus, right? So we have gotten too hot, right? We have some sort of stimulus. Basically, we've left the range. A sensor is going to detect that we have left the normal range, that we have gotten too hot or too cold or whatever. And then from there, that sensor is going to send that information to the control center, namely, in most cases, we're talking about the central nervous system. And then the control center is going to send out a response to an effector. And an effector is just any part of the body that will cause a change. It will cause an effect. So that could be like muscles, that could be glands, that could be some sort of organ, whatever needs to receive that message to cause a change, right? And then in essence, that will cause us to do something that will bring us back to the normal range, right? And then we go back to the stimulus. Hey, if we're back in normal range, the sensors can detect that. They can tell the control center. The control center can then tell the effectors, hey, you've done your job. You don't need to do any more. And if we swing the other way, right, we go too far in the other direction, sensors can detect that as well. Control center can deal with that and send out a signal to maybe a different effector to cause a different effect to bring us back up to our normal range. So that might sound a little bit jumbled because we're talking very generically about this, kind of generally about this, but let's talk about a specific example. So we're talking about body temperature here. So in this case, our stimulus is that our body temperature has gotten too high, it's too hot. So we have cells, we have sensors in the skin and the brain that can detect that the body temperature has gotten too high. And so then they will send that information to the brain. The brain has a center that will kind of help determine our temperature and whether or not we're too hot or too cold. And then the brain can send information to things like sweat glands, right, throughout the body and say, hey, you need to release sweat to cool us down. The sweat glands receive that information, they receive that instruction basically. They start to release sweat. The sweat has a cooling effect, and so our body temperature will then decrease because of the sweat. If the body temperature goes too low, right, same thing, we have sensors who can detect that. The sensors then talk to the brain, the same region, right, temperature regulatory center in the brain. And then instead of talking to the sweat glands because we're now too cold, sweating's not going to help. Our brain can maybe talk to muscles. Hey muscles, we need you to shiver because the little tiny contractions generates heat. So it can talk to the muscles and say, hey muscles, you need to go ahead and shiver to generate heat. Our body temperature then increases. And so it's kind of almost like a teeter-totter in a way, or a seesaw, where we are kind of performing a balancing act. And if we swing too far one way, we're going to cause an action that brings us back to normal. And if we swing too far the other way, we have another action that can swing us back into the middle again. And so we're just constantly kind of playing within these normal parameters, making sure we never go too far in either direction, right? Because if you are on a balance beam and you swing too far to the left or the right, you're going to fall off the balance beam. If you are on the balance beam and you start wobbling towards your right, you're going to cause actions within your body that kind of dictate you towards the left to keep you on that center line. If you are swinging towards the right and then you kept swinging towards the right, you would just fall off the balance beam, if that makes sense. Now, positive feedback is less common but still important because there are some cases where we don't want to stay at the set point. We do want to cause immense change, and the best example of that is childbirth. Childbirth is positive feedback because we want to encourage that baby to be born. So in this case, right, we'll talk about the cycle, and I'm just going to start with the baby's head pushing against the cervix. So I'm starting over here on the left. So the baby's head is pushing on the cervix, right, head facing down, and that stretching of the cervix is going to send nerve impulses to the brain. Those nerve impulses to the brain are basically going to tell the brain, hey, we're trying to have a baby. And the brain, in response to that, is going to tell the pituitary gland, hey, secrete a bunch of oxytocin. The oxytocin is pushed into the bloodstream, it eventually reaches the uterus, and when the uterus receives oxytocin, it's going to cause uterine contractions, basically kind of squeezing around that baby to push that baby further into the birth canal. So baby's being pushed up even harder against that cervix, which causes more stretching, which sends more nerve impulses to the brain, which then the brain tells the pituitary to secrete more oxytocin. More oxytocin gets to the uterus then contracts even more because of the higher levels of oxytocin. That causes even more pushing and stretching against the cervix, more impulses to the brain, more oxytocin being released, more oxytocin being received by the uterus, more contraction. So you can see it's kind of like a runaway train in this aspect, in that the actions are all feeding into each other and it's cyclical. We're going around and around and around. And this is going to happen in this case until this baby is born and the cervix is no longer being stretched, right? Because there is no baby to push and stretch it anymore. Right? So in this case, positive feedback is good because it's allowing us to have this baby. We don't want to keep the baby in there forever, right? I'm sure anyone who's ever been pregnant has gotten to a point where they're like, get this kid out of me. And so in this case, right, this cycle, this positive feedback loop is to promote labor, to promote birth, and then once all is said and done, then positive feedback can shut down.